So good morning. We are now going to consider the second problem. This is the second problem in the board exam. This is a very interesting problem, and I'm very challenged in this. I would like to share it with you how to solve this board exam. Yeah. So this board exam problem states that there is a rotary dryer fired with the bunker oil or the fuel of 10,000 kilocal per kilogram. And what's that? Higher heating value is to produce 20 metric ton per hour. Metric ton per hour of dried sand with the 0.5% moisture from wet feed containing 7% moisture. Specific heat of sand is 0.21 BTU per pound per degree Fahrenheit. And the temperature of wet feed, meaning the fluid, is 30 degrees centigrade, and the temperature of dried product is 115 degree centigrade. So this is the problem. Okay. First, we have to jot down all the given uh, data or the known data. So let me start. So here is metric ton. No, metric ton. Okay. So here are the questions. The question is number one. Calculate the weight in kilogram of wet feed per hour. So calculate in kilogram per hour the wet feed. The wet feed. The number two, calculate the weight of water to be removed per hour in kilogram. Calculate the weight of water to be removed per hour in kilogram. The number three, calculate the heat in BTU per hour required, meaning the output. Yeah, the output of the the heater, the output of the heater that is required to be delivered to the dryer. Okay. Now calculate liters of bunker oil per hour, meaning calculate the volume flow. Okay, volume flow rate, meaning liter per hour of the fuel, because when you talk about the volume of the fuel, it is in liters, especially in the metric system. If the specific gravity SPGR of the bunker oil is 0.9 and dryer efficiency is 60%. Okay, yeah, yeah. So those are the problems. Now we go back here in this page, yeah, and then we are going to have some space here so that we can write the space available. So, first, what do we know about this problem? What are the known data? What are the given parameters and the known data? So, we'll have it one by one. Let me use the white. Um, so here, first, the type of dryer is rotary. So, as we know, there are two types, general types of dryer. One is rotary, rotating, and the other one is flat bed. So, in this case, we are in rotary dryer. For those who have of you who have not yet seen or those who are not yet familiarized with who have not yet familiarized with the type of dryer, this is the rotary. I made the research, and when I was working with the DOST MIRDC, we had the problem. We had the project in with the coconut drying, coconut processing, coconut cocoa wire, coconut husk. So I was able to visit University of the Philippines, Los Baños, and there is the another agency of the OST, which is the PICARD, Philippine Council for Agricultural and Aquatic Research Development. I before I was able to buy this book, Rotary Flash Dryer, by a very good author, engineer, uh, Dr. Alexis Bilonio. I guess he has already the PhD, and this is a project of Philippine Council for Agriculture, Forestry, and Natural Resources and Development, and of course with the uh, with the support of TAPI, the Technology Application and Promotion Institute, yeah, of the DOST. So here is the kind of rotary flash dryer, yeah. So it is here, the parts, no, there's a hopper, there's a rotating cylinder, there's a stationary cylinder, there is an oscillating cooler, centrifugal blower, yeah, to blow the heat, and also hall furnace or gasifier or dust and ash collection systems, and the prime mover, which is the motor. There are also conveyors and elevators, bagging, and the tempering bins could be added component as a component for easy operation of the dryer. So in this case, there is this ash. What's this? The furnace hull, rice hull furnace or gasifier. Yeah. So the other they are using steam. Now this one is a gasifier from a rice hull. So to give you an idea how this palay or paddy rotary dryer works, this is the design, and this is the more clear, larger view. So what is important is there's a feeding place, which is the hopper, number 9, if you can see, yeah. This is the chute or hopper. Then here is the rotary dryer, the drum. Yeah, there's stationary and there's a fixed drum. So you put the feed, and then when it goes out, it becomes the product with a less moisture content. Here is the wet feed. Then here is the lesser moisture content product, feed product. Okay, so mm, if I may illustrate this here, so you feed the sand or the whatever the sand. You can feed whatever you want, sand or the grain, yeah, the palay. Then after that, it will go to the discharge. Yeah? So here's the blower, centrifugal blower, and then later on it will somewhere it will have some kind of discharge there, right? So feed here, and the product is discharge, yeah, at the output, no? So here, that is the story of the the rotary dryer. So for example, feed, then product. Okay, so that is a brief background. For others, it is included in this slide, and we don't have time for that. Yeah, it's more on the agricultural engineering side. But here I put the different kind of the types of rotary dryer here, and their picture, yeah, from different places, and the design of the rotary dryer for your reference. So there's a shaft, there's a drum, fixed and stationary. Yeah, rotary flush palay dryer. Yeah. So this is the feeding bin or hopper. Then of course it will be discharged at the outlet of the dryer. Okay, so that is just a brief background of our rotary flash dryer. For those who are not familiar, it's for those people who are students or teachers that have not yet seen in their lives, in their entire life, the rotary dryer. Here it is, right? So I have the book. I just get the camera from there a while ago. So here is the how the flash dryer works. Yeah, it is explained here. I put the website like this. Yeah, process heating and the rice knowledge bank. Yeah, so which uses a flash dryer. Yeah, so to give you an idea of what a rotary flash dryer is. Yeah. Now, our concern is not more on the design of the dryer, but it's more on the problem solving of the drying process. Yeah, it's not the mechanical design. I mean the the fabrication parts. It's not that. It's more on the process design, which is the drying or the air conditioning, the thermodynamic properties happening in the dryer. So it's a rotary dryer, and then there is a bunker. So what do we know the bunker? Yeah. So type of dryer is rotary. Then this the type of fuel, right? So we know that the bunker is fuel that is a low grade. Yeah. So it's like when you are trying to have this process of oil and gas, and then if you process this oil, which has also a gas at the same time, the lower part or the heavy part is the the diesel, and the last part is the bunker. Yeah, so it is really a low grade, no? Low grade, maybe low octane fuel used for burning, right? So what else do we have here? We have of course bunker oil. This is an oil, and then here is to produce 20 metric tons per hour, but here is the heat. Mhm. The heat of oil. I mean, the higher this bunker oil has higher heating value of 10,000. What's that? Calorie per kilogram, HHV. So HHV, what is HHV? Higher heating value. There's another measure of heat in combustion that is lower heating value. So if you are an engineer, maybe like me, I'm a mechanical engineer. I have subject like combustion and also this power plant. So when you talk about power plant combustion, no, so you will encounter this lower heating value and higher heating value. To cut it short, higher heating value or heating value first. Heating value is the measure of heat that is being released during combustion. And higher heating, lower heating, it just depends on the hydrogen content of the fuel. And higher heating value is based on the so-called condensate or liquid. Now it accounts the liquid in the process, the condensate, because when the product of combustion is carbon dioxide and heat and water, there's always water in the combustion, no? It's very amazing that the liquid part is always there. Now lower heating value is more on the measure of the product of combustion, the heat released during the combustion, but it is based on the so-called mm, vapor or steam. Yeah. So vapor or steam, you are dealing with lower heating value, but higher heating value is more on the liquid or condensate. Anyway, I have put some slides to enlighten our viewers, our watchers, like this heating value of a substance is also called energy value or calorific value. Usually a fuel or let us say food energy is the amount of heat released during the combustion of a specified amount of it, no? Amount of a substance. Now, here, higher heating value is more based on the water, yeah, original and generated water, yeah, in a condensated state, meaning fluid, while the lower heating value is based on the gaseous water as the product or steam. Gaseous state of water is steam. Again, here the lower heating value, yeah, that treats this treats any water formed as a vapor. So as I told you, it's more on the vapor consideration, while here is more on the condensated state of water or the liquid. To emphasize again, higher heating value assumes all the water component is in liquid state. No? The water component as the product of combustion is in liquid state na at the end of combustion. But here, lower heating value. Yeah? Lower heating value, look at this, water is condensated, uh, higher heating value, but the lower heating value is steam, yeah, vapor. Then the heating values is lower, yeah, lower heating value. When it is considering the water as a condensated the form, yeah, it is higher heating value. Yeah, so it's just an additional knowledge for those students and teachers. How do we differentiate the higher heating value and lower heating value? But I think in this case, we are considering higher heating value. What else do we know on this problem? What are the known data? Of course, we are trying to dry the material. Let me write it here. So the material in question or the subject material is sand. Now, everybody knows what is sand. Now, let me dissect it further. What is the weight or the mass in the pro product or produce at the output? So here, so if you have a feed, yeah, feed, then you have here going out at the discharge is P, product. This is the feed, yeah. So it says here is to produce 20 metric ton, yeah. So it's missing. I miss the writing of this very important metric. Where are we? Here, metric ton. So when we say metric ton, m ton. So we know that metric ton is long ton, which is 1,000 kilogram. So metric ton per hour. Yeah. So 1,000 ton per hour, but there's a number before that, 20. So 20 MT, no? So if we have 20 metric ton, we have 20,000 kilogram per hour. Okay. So where is that 20,000 metric 20,000 kilogram per hour? So here at the product there is 20 metric ton. Okay. So now this 20 MT of sand is the product, and it's the P, right? What about the F? The F is the mass flow at the feeding side. Yeah. So this one is the mass flow rate at the discharge side or product. So product is discharge side. Feed is the feeding side. Yeah, the entry side, or the feed side, the entrance, right? So here we have P, but we don't have F. What can you say about the relation of P and F? For sure, F is more, right? So F is greater than P, yeah, because here is wet, right? So being wet, it's heavier, it has more weight, or it has more mass flow, right? So F is greater than P, yeah, but here only P is given. Now we continue to dissect the known data with the 0.5% moisture. Now we're talking about the produce or the product. So we are on the side of the product here. 0.5% moisture, and then coming from wet feed containing 7%. So here, when it was already dried, there's a 0.5% moisture. So that is percent MP. Yeah. Here at the feed, there is 7%. Percent. That was this MF. Yeah. Percent MF moisture content at the feed is 7%, while the moisture content of the discharge or at the product after the dryer is 0.5%, which is expected. Now, so meaning there should be less moisture content at the discharge or the at the product side compared to the feed side. Now we continue. Then it says specific heat of sand is 0.21 BTU per pound. Mm. So it says specific heat of sand. Yeah, so meaning, let me put it here, CP of sand is 0.21 BTU per pound per degree Fahrenheit. Of course, we can see, or we can convert that, or we can also see that right away or immediately in the internet. Now, what is the specific heat of sand in terms of kilojoule per kilogram degree Kelvin? Now, so or we can convert. There's no problem with that. So now, temperature of wet feed. Now, so I would like to to emphasize this, temperature of wet wet feed, yeah, wet feed meaning liquid, yeah, wet feed. So this is liquid. Is 30 degrees centigrade, right? 30 degrees centigrade, and the temperature of dried product is 115. Okay, so the temperature of the dried product is 115, meaning it's higher. Yeah, the temperature at the product is higher, and this is the temperature at the at the feeding side is lower. Okay, so there are other given or known data which are available or given in the question. So let me go into that. Look at this. Calculate the weight in kilogram per hour of wet feed. Right. So here we will just have to annotate this. Well, once we hear this weight, no, in engineering sometimes the terms are interchangeable, like weight and mass. No, for example, as long as the gravity is not yet is concerned, it's not concerned. So weight and mass could be interchangeable. So what we're talking about here is the mass. Yeah. So mass flow, or the weight flow, mass, kilogram per hour. So mass flow is kilogram per hour, right? So the unit is kilogram per hour. So weight, yeah, or how much quantity of in kilogram is flowing per given time, which is in every hour. You can also convert that in a minute or seconds. There's no problem. But here, what is being asked in the board exam is the kilogram per hour, right? The number two question is calculate the weight of water to be removed per hour in kilograms. Yeah, meaning in kilogram for every hour, what is the weight of the water? So weight of the water, or it's also on the mass. Yes, that's the mass flow. Yeah, because kilogram per hour is mass flow rate. Yeah, mass flow rate of evaporated water. Okay, so we know that if you put sand, wet sand, then it will become dry. So the moisture content will be reduced. No, so that means what is being sought here is the mass evaporated, no? M sub E, which is simply the feed minus the product, meaning the kilogram per hour in feed minus the kilogram per hour at the product side. Then you will get the amount of water, yeah, the weight or the mass of water to be removed or being removed. Yeah. So this is clear, number one and number two. Yeah. So both of them are mass flow rate, or weight in per unit time. Now, the number three question is calculate heat in BTU per hour required. So this number three is a bit complicated because in order to get the heat, you have to dissect, you have to analyze the all the heats that are involved in that, right? So if I may ask you, what 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 are the heats that are involved in this problem? What are the heat that are involved in this problem? I want to discuss this because I want you to understand the detail of the problem. That it is not that easy. It is a bit complicated. Now, so when I ask you what kind of heat is being asked in this, anybody, anyone, what kind of heat is being asked in this problem. So the heat that is being asked is the output output the heat output of the steam that is going to be used as a supply to the dryer, meaning that the output of the the steam or the heater that is going to be the input to the dryer. And it's not that easy because you have to analyze the composition. You can decompose the sources of heat. No? And based on my calculation, there are three sources of heat there. One is heat required to evaporate. I think we oh yeah, the heat required to evaporate the moisture, yeah, from the wet sand, and to become the dry sand. That's number one heat. Number two heat that I put here, the number two heat is this heat absorbed by the sand from 30 degrees to 115. Okay, so meaning first the heat that is required to evaporate the moisture, meaning from 7% to zero point 0.5. We have to have a heat to evaporate the moisture. The other is the heat absorbed by sand from 30 to 115 degree centigrade, because the sand initial temperature is 30. If I may emphasize, where is that? Here. So the sand, let me use another. Yeah, the sand on the feed or wet feed side is 30 degrees. Yeah, wet feed, and then it goes out as here 115 degree centigrade temperature. So there's a delta T or change in temperature. So there's a heat transfer there, right? So that's another heat, and the other, based on my calculation, is the heat. There's a heat absorbed by the moisture that remained in the sand. Yeah. So after the drying process, there's still heat. Yeah, in the sand now absorbed by the moisture, because the moisture at the output is what, 0.5%, meaning that's the water content, 0.5. There is a 95 a 99 point what point 5. There's 99.5 percent dryness. But when it first enters the dryer, in the feed the side, there's a 7% moisture content, meaning 7% moisture. There is a 93% dryness. That 93% dryness. Yeah. So there is this number three, meaning there is this number three heat that I calculated, and then this is the heat absorbed by the moisture that remain in the sand. Yeah, because there's a remaining moisture, and that is 0.5%. So all these three, when you add all these three heats, it will be the summation of heat that is being required, which is the output of the heating system. Now, if they are using steam, right? So that is the required heat, yeah, the output. And then in this problem, the efficiency is given, so you have to divide the total heat with that efficiency, I think it is 60%. Yeah, right. This one. So 60%. So you have to divide that output to 60% so that you can see the input. Yeah, because it has an efficiency, and you will see that the input is larger. Yeah, before it delivers an output to the dryer. And the number four is calculate the liters of bunker oil per hour. The liters of bunker oil per hour. Uh, and there's a specific gravity that is given, which is the specific gravity of bunker oil is 0.9, and the dryer efficiency is 60%. So for me, it's a bit complicated. There's a lot going on. There's a lot of information in this problem. Okay, I think the problem is pretty clear. The question is, how do we start? How do we start? Of course, how do we formulate the attack or the approach of the solution, the approach to this problem? So now, I think that the first thing to do is to draw the system, yeah, or illustrate, and then put down the given, right? So here is the illustration, right? The illustration. So here is the the rotary dryer, and the rotary dryer has two sections. I told you, one is feed, mhm, the feed side, no, F, and here, yeah, the product or the produce or producing segment. Yeah, what is being produced here is a dried product or material that has less moisture content. Okay, so this portion here is the feed. And what kind of feed? I want to emphasize this is wet. Yeah, wet, wet feed, wet feed. Yeah. So here there's an arrow here, and of course there's an arrow here. The discharge product. Okay. Now there is fuel. There's a fuel here, right? The higher heating value, higher heating value, which is based on the condensate or water form after the combustion, as compared to the lower heating value, which is based on the steam or gaseous state, no, as the product of combustions of the water. Yeah. So here the fuel, yeah, here of course you put fuel, no, to the system, no. For example, in the steam, you put the fuel with this heating value, and then the water will be converted into the steam, yeah, that will heat up the sand. Yeah. So here is the fuel, yeah, fuel. The higher heating value is 10,000 kilogram, and then so it will go out here, right? So the heat will come out, yeah, and then here the sand, uh, you will feed the sand, yeah, and it will rotate, yeah, it will rotate, while you are feeding the sand, right? Then here is, as you can see, it is inclined, that there's an angle somewhere here, so that for easy flow of the material now by gravity, you can control the flow and the speed when you control the angle also. Now, what are the other given? The other given is this. Yeah. So here we expect that the P, or the mass flow, or the weight, in terms of uh, mm, kilogram per hour in the product side is this now, 20 metric tons. So we know that the 20 metric ton is a long ton. Metric ton is 1,000 kilograms. So m ton, mt is 1,000 kilogram. So mt and nt. So it becomes 20,000 kilogram, yeah, per hour, because it says is per, here in the problem it is per hour, right? Here, 20 metric ton per hour, yeah, produced, meaning at the product site. So we are clear on that, and this is this. Another thing that is given to us is the moisture, yeah. So the percent moisture of the product is how much? 0.5%, meaning there's a 0.5% water content. So what is remaining, or the dryness, is 99.5% dry. Here at the what is this? At the feed side, there is 7, because it has more moisture content. 7% water content. So there is 93% dryness here. Okay. Now here, the initial temperature of the sand is kind of ambient, yeah, or within that range, 30, yeah, 30 degrees centigrade. But once, yeah, once it passed through the the rotary dryer, then it was discharged. It becomes what, 115. So there's 115 increase temperature, from 30 it becomes 115, because it is subjected to heat, and the heat energy transferred to the sand, so that the moisture or water content evaporate. Now it will be evaporated because the heat is being transferred, so it will displace the water content, so that it becomes dry, and moisture content will be less, from 7 to zero point 0.5. I think our illustration is uh, clear, right? So we could start with the first problem, I guess. So our first problem, a question to be solved is this: now, calculate the weight or the mass in kilogram per hour. Yeah, wet feed per hour. Calculate the mass or wet feed per hour, and then the number two is calculate weight of water to be removed per hour in kilograms. Yeah. So here is the number one, right? So here is just the additional information, the higher heating value, what is heating value, and what is low heating value from Wikipedia. So a proper citation is there, yeah, so that we avoid the copyright issues, right? So we cite properly where we get the information from Wikipedia. This is also from Wikipedia. Now, here is the solution. So how do we how do we do the solution for the problem. So let me discuss the solution to to the first problem, and let me let me take some space here. Yeah. What is being asked here is actually the mass flow rate at the feed site. So let let us review the some some of the basic formula which we have already uh, tackled here, right? So here. So we have an equation here. Let me just get the equation here and paste it here on the other side. And put that in the full presentation. There we go. So the governing equation is this, and what is this all about? Is this the principle of conservation of mass? Yeah, principle of conservation of mass. So conservation. So meaning the bone dry mass (BDM) of the feed is equal to the bone dry mass of the product, right? So here is this now. Now, what is this all about? Is very simple. So F is the mass flow or the weight, no weight in terms of time per hour. So mass flow rate or weight flow rate, if you could say like that. So F, yeah. So F is like this. So the flow of the material in the feed side per hour, kilogram per hour, is multiplied by 100%. Yeah, 100% dryness, because we are talking about dryness now. So 100% minus percent of the moisture at the feed is equal to the mass flow rate at the product side or the discharge side multiplied by 100% dryness minus percent moisture of the product, right? So what is being asked is, I think, the mass flow rate at the feed. Let me go back quick to the question. Calculate the weight or the mass in kilogram of wet feed per hour. So it's a wet feed now. So what is the kilogram per hour of the wet feed? Of course, in this equation, that is the F right here. So this is the mass flow rate at the wet feed. Okay, so let us plug in straightforward. We've plugged in the given values. So we have F that is being asked. So 100% dryness, yeah, minus percent moisture of the feed. What is the percent moisture of the feed? 7, right? 7%. Then it is equal to the mass flow rate at the product or at the discharge after the dryer. So what is that? 20 metric tons or 20,000 kilogram per hour. That is the flow, mass flow at the discharge or the product. Then, of course, 100% minus the percent moisture at the product is less, less than 7 because this the feed is the product. So I think it is point 0.5, right? 0.5%. So moving on, feed 100 minus 7 is 93% equals 20,000 kilogram per hour. I'm not going to put the units to simplify things. 100 minus 0.5, 99.5%. Okay, so we convert the percent into decimal. When we go to mathematics, the percentage should be changed into decimal. So F times how much this? 93 over 100 is 0.93 equals 20,000. Then, of course, 100 minus 0.5 is 99.5 divided by 100, it is 0.995. So F now, or the mass flow rate, is what? 20,000 times 0.995 all over what? All over 0.93, right? Okay, so we will show this to you. Yeah, so let me pull out my calculator in my laptop so that each one of us can see. Ano nangyari? It's happening to this mouse. So I have here a calculator, and we could use this calculator. Scientific, right? So I have here 20,000, 1, 2, 3. So we have this. You can see in our screen times 0.995. This is the answer. Divided by, we have a divided by sign here, 0.93. So what do we have? 21,397.849. Let me jot this down. So we have a mass flow. The feed is 21,397. Then we rounded off 85 because it's 849, right? So this is the answer. So same as this, same here. Okay, So 21,397.85 is the mass flow at the feed side, which is expected, na? Because the feed side should be greater than the product side, because the feed side still have a moisture content. When it goes to the product, the moisture or the water content will be removed, so it should be less mass in terms uh, with respect to hour or against the hour. Okay, I think it's clear. Now we go to the second. Let me erase everything so that we have space. Okay. So the second question is, what is the weight or the mass of the water removed? Or what is the water content that is removed or evaporated? So the other notation for this is M sub E. Mass of water or mass uh, evaporated, ME. Now it's just simply feed minus the product. So when you subtract the two, the difference will be the amount of water that is evaporated or removed or extracted. No? So we already have the mass flow rate at the feed. What is that? 21,397.85 minus the product. Now the product output is 20 metric ton. That is the design. That's the target. Yeah, 20 metric ton meaning 20,000 kilogram per hour. So both of this has the unit of kilogram per hour. So when you have this 21,307.85 minus 20,000, it's easy. Yeah. So you can get, no, without using calculator, 1,397.85, yeah, kilogram per hour. So that is the amount of water evaporated or removed, no, because it goes into the air, it evaporates. Okay. So we already solved the first and second. So one is the mass flow at the feed, and the other one is the amount of water being removed or evaporated, right? Now, this is the challenge, number 3. What is number 3? Question. Let me go back to the question. Lists. Calculate the heat in BTU per hour required. Calculate the heat in BTU per hour required. As I told you, there are 3 um, sources of heat so that you can get the total heat output. No? What do I mean by output? Let me clear this. Here is the source of the heat. No? So here is the source of the heat. So here is the heater. It could be steam, right? So there's a mass of steam, then it goes out here, yeah. So there's a enthalpy here, yeah. So mass of steam, then enthalpy of steam, no? It's because the energy or heat energy is there as an internal energy into the uh, enthalpy. It can be read in the steam table. And why steam table? Because it's a wet sand, right? So it's a wet sand. There's a saturated saturation point of vapor and saturated point of fluid, and we will discuss that. Yeah. So what I'm after is this. So in this block, so this the heater side, then it goes to the dryer, right? The dryer side. So here, the heater here is the Q total. Uh, Q total is the so-called output, no? So the output, the heat output is the one to be used in the dryer. So the output of the heater is the input of the dryer. Again, the output is the output side, and this is the input side of the heater. Yeah, so heater input or Q input here, and Q output is the total. For example, the total. Yeah, Q output is here. It will be the input to the dryer, right? And the dryer, you put the material, the sand, and then the temperature will be high, right? The after after the output, the temperature will be higher than before, and it depends on the problem given in the problem, but in this problem the temperature will be higher. So from 30 it becomes 100, I guess. Let me go back to the given to be sure. Yeah, 30 degrees centigrade wet feed 215. Okay, so here 30 degrees centigrade, then it becomes here the sand. After the sand is being put in the rotary, it becomes 115 degree centigrade. Yeah, but of course there's happening in this process. Yeah, because there's a water will the water will be converted to steam, right? So there's a process here that we need to resolve. Now, where do we start? First, we need to get the properties at the steam table. HF at 30 degrees centigrade, meaning enthalpy of fluid at 30 degrees centigrade. So we have here 125.79. Then enthalpy of gas at 100 degrees centigrade. Why 100? Because the saturation point of water is 100. Yeah, before it becomes steam, it will boil when it reaches 100 exactly. 100 degrees centigrade of water, it will boil. And then after it boils, it becomes 100 degrees centigrade steam or vapor. Yeah. So water evaporates at 100 degree centigrade. No, no more, no less. Then the other one is enthalpy of fluid at 115 degrees centigrade, which is 482. 482. Yeah. So why do we need those figures? So we need to know where do they come from, and they come from the steam table. Yeah, because there's a water side and the fluid side, and also there is this delta T happening. Yeah, there's a change in temperature. So let me put that. Yeah. So I think we have to jot down the different temperature so that we can see for ourselves. So here is 30 degrees centigrade, and then 100 degrees centigrade, and then what is that? 115 centigrade. So let us use the internet. Let us see if we could get something from here. Steam table. Was this 30 degrees? Yeah, enthalpy. Yeah, so the enthalpy HF at saturated. This is saturated. Right? 30 degree centigrade. Because I don't have a steam table here. we could see from the internet temperature 12.01 up to 150. Then this one is Keenan and Case, New York. This is the more familiar to me. Yeah, Keenan and Case. Yeah. So saturated water table, meaning saturated, meaning it is HF at what is this, 30 degrees. Oy, what the heck? It's temperature. We will 30 degrees centigrade. Um, Let me use the meaning SI. Yeah, SI units. SI unit property tables and steam tables, Michigan State University. Is this SI? So let us see. What is this? Saturation temperature table for steam in SI unit. So our temperature is this is saturation, no? Saturation at 30. So we will look at 30, 30, 30, 30. What is this? 30, and then we will look for 30 degrees centigrade, and then 30, 30 degrees centigrade, and then we will look at the I think we will look. Wait, is this centigrade? No, we have to look at 130 now. HF. It is the fluid, because it's a fluid side, because it's a wet feed, right? So there's a water content at 30 degrees centigrade, so we will get that the HF. So where's the HF? We have, let me zoom in, control plus plus. Yeah. So HF, HG, HFG. That's HF at 30. 30 HF. Here. Yeah. HF at 30. 125.811. Is that correct? 125.811. Correct. Yeah, 120. The here is 125.75. There are some kind of variances, but if it's only less, there's no problem. Huh? So I put in other tables it's 125.78, but it's near. Yeah. So let me have this 125 point the 30 degrees. Yeah, 125 point 811. So if you have this temperature, then you will have a saturated pressure of 4.24. Yeah, pressure. Yeah, so let me capture this so that we will have kind of evidence, right? So let me cut this, right? Because it's only HF. Yeah, yeah, HF, because HG we will get the HG in the 100. Why 100? Because that's the temperature of the of the boiling. Yeah, 100 degrees centigrade. So let me go back to this, and let me paste it so that we can have this as our data. So when we get those data, where are we? This one? Yeah, this one. So I'll put it here. Okay, 30. Yeah, 30. Okay, so I'll make a blank space because I want to get now the enthalpy of gas at 100 degrees centigrade. No, so Hg, meaning Hg is the enthalpy saturated vapor at 100. So let me put this. So enthalpy of gas at 100 degree centigrade. Yeah, so please bear with me because it takes longer time. So we'll go back to this. Yeah. So 100, we go to 100. And then what column is this? 1, 2, 3, 4, 5, 6, 7. Seventh column because enthalpy of gas at 100. So here is 100, right? Here is 100 and the column is 7. 1, 2, 3, 4, 5, 6, 7. So we have 267 5.84. Let me check with my number. So it's 2676. 26 76 2676, and there's some kind of difference, but it's less, right? So 100, this is 2675. Now if you are going to this off, rounded up 2676, it's okay. Yeah, so let me capture this. Yeah, so that's serve as an evidence. Yeah, so here let me capture this. Yeah, 100. If it's 99 or 101, it can be interpolated. So it is 2676.1. Here is 2675.84, right? Yeah. So let me go here. So here, yeah. So now that is the first um, data that I will be needing. So let me go to the presentation so that I can explain this very well. Okay. So here from the steam table, so it is a steam table like real time. It's from the University of Michigan. So when you get the other data from another table, it might have some variances or differences. It's like a point zero zero something only, no? But more important to me is that if it's less variance, no, it's okay as long as the process is correct, and we could we could put considerations in the range. Yeah. So here 30. Yeah. So 30, you go here, 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 right? Because it's HF. Why HF? Because it's fluid, no, saturated fluid, right? So saturated fluid. So we will have this value of the HF. Where are we here? Okay, 125. What do we get? Because this is my old notes. This is 125.79. No? So if you rounded this, it becomes 125.9 and 7 is 8, right? 125.8. It's pretty much near to this, right? So there's no issue. 125.8, 125.811. No? So the other one is Hg at 100. Now, why do we use 100? Because water evaporates at 100 degrees centigrade. So when the steam is applied to that sand, so the water in the sand will boil, and the water starts to boil at a very specific temperature, and that is 100. So 100 degrees centigrade is the saturation temperature of the water. It starts to boil, and it boils, then it becomes 100 degrees centigrade steam or vapor. So there's no change in temperature. That's why it is called latent or latent heat of vaporization. So there's a 100 degree centigrade water boiling, it becomes 100 degrees centigrade steam or vapor. So that is saturation. No, saturation means um, uh, latent or saturation, meaning there's no change in temperature. You cannot measure because there's no difference. How can you measure if there's no difference? It's the same. So there is no difference in temperature, but there's a difference in phase or form or state. Yeah. So the water, boiling water, becomes vapor. So there's a latent heat of vaporization. So let me go to the next. We also get this. Yeah. So 100. This one is 100 degrees centigrade, and this one is this is the Hg, meaning enthalpy of gas at the saturation line of vapor. So here there is a 2678.95. And what did I get? Because this one, I solved this one like years ago. I just pull it out from my old notes, to be honest. So this one is, what is this? 2676.1. So the enthalpy of gas saturated, the temperature of 100 degrees, 100 degrees centigrade, mm, saturated temperature, because it can no longer hold the vapor. It will become vapor. Yeah, it can no longer hold the vapor content. It will become gas. So the 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 value is 2676.1. So let us see, 2676. So we'll just have to round off. Yeah? So if you round off this, because it's, there's some difference in different kind of tables coming from different sources. So if you round it up, 0.95, 2678, not 2678, uh, 0.95. So this one is, I guess, what is this? There's a difference sometimes in, yeah, there's a difference in the data. Yeah, so 2676.1. Well, there is 2678. I guess there are kind of like a two. Yeah, 2676. Yeah, 2 points. Yeah, 2676. So anyway, still it's near. Yeah. So it's what we're trying to say here is that there's a variation in terms of data source. Yeah. So 2676 kilojoule per kilogram. So I just showed it to you so that you have an idea where are we getting the data, right? So it depends on the source where you get it. Yeah. So assuming, so that we can simplify the process and the calculation, assuming we abide by this data now from my old notes, so that it's already calculated. It's hard to calculate again and again the different data source. So we just follow this for a while. This 2676.1. Then again, we are going to calculate the wet feed. Yeah, here. What is the enthalpy of saturated fluid at 115 degrees centigrade? So let me go back to the internet and uh, let me find this 115, right? So 115. What's happening to this mouse? Kind of stuck up here. So let me go back to the internet and 115, right? So still it is on the seventh column. 1, 2, 3, 4, 5, 6, 7. Enthalpy of gas, but here 6, right? Enthalpy of fluid. Enthalpy of fluid, right? Enthalpy of fluid, 100, what is that? 115. Enthalpy of fluid at 100 fluid at 115 degree centigrade. So we will have that enthalpy of fluid at 115 centigrade. I have here in my notes it's 482.48. So let me put here 115. Oh my God, it should be interpolated, right? So enthalpy of fluid. So 478, 486. It's between 478 and 486. So let us abide by this 482.48. So let me capture this first so that you have an idea of what is going on. So here, let me capture this whole thing because it's 115. So enthalpy of fluid, right? Then let me paste that here. Let me put this, yeah, this one. Then we'll just copy this, and then we'll change something. So enthalpy of fluid, because it's a wet feed, at 115 degrees centigrade, and then we go to the um, we go to the full yeah, here. Okay. So now here, I think what I have to do is to erase. Yeah. So this is 115. Let me use another pen that is more um, visible. So we are concerned is 115 saturation temperature, and it lies between 114 and 116. No? So 115 degrees centigrade, and then you are trying to project horizontally until you reach the HF. So here is the HF, enthalpy of fluid at saturation point. So let me draw the line um, going going downward. No? So let me put the line. Yeah. So what you have is here. So let me put this. So at 114, you will have what? 478.038. Then at 486, at 486, at 115, this 115 you don't have, right? Because it's in between the two. But at sorry, 478. So this is at 116 degrees centigrade. You will have 486.516. So here is your blank x. So what do you do with this? What do you with this? There's a process in mathematics, elementary mathematics. Let me erase this. So we should erase this to avoid the confusion. So there is a process in mathematics called it's called interpolation, right? So you can solve this by the process of interpolation. Okay. So how do we interpolate? So we can have this like this one and this one. then this one, right? This one and this one, it should yield into positive. Yeah, so let me show that to our viewers so that they will have an idea of what is really going on, right? So by interpolation, we can have this, right? And then we will solve it right uh, in our face. How do we get this, right? So equals this. So we have in the numerator we can have this, yeah. So because it's just like a one-on-one correspondence, so it should yield to positive if the numerator is 115, like 115 minus 114. So this one, yeah. Then the downside, the denominator is 116 minus 114, right? So here, right? So this one is x minus 478.038. Then here, you go there, you subtract the two fours, 4, 8, 6.516 minus this one, yeah, 478, right? Minus 478 .038, 0.038. Okay, so this is by way of interpolation, so that we can see and then we can compare to the old notes that I have, right? Interpolation. So let me pull out our calculator, yeah, our calculator. Let us pull out. Let me check if this is still recording, right? This is still recording. So let me pull out this calculator so that we can show to all our viewers what is really going on with this mathematics. So let me put here very near, right? So sorry, clear. First, this one is no brainer. 114 minus 115 minus 114 is 1. 116 minus 114 is 2, right? So I'll put this. Let me put this above. Yeah, let me pull out the more striking color. So here, this here we could transfer it here, right? So at the numerator, 115 minus 114 is 1. 116 minus 114 is 2. Then it is equal to x, right? X minus 4, 7, 8. The lower side, lower limit, 0.038. Then here, let me do this thing here. So we'll put that in the calculator so that everybody can see, yeah. So what we have here is 4. Let us clear this first. 486.516 minus 478.038. Are we correct? Well, yeah, 478.038 now equals, right, now 84. Let me jot it down for you. Let me jot it down carefully. This one here. Okay. Where are you? Where is this calculator? Where have you been? 8.478. 8.478. 8.478. 8.478. So all we have to do is cross multiply. So we cross multiply. So 1/2 is zero point 0.5. Yeah, so we just multiply this here to the 1 divided by 2. Then we add the whole this, yeah, to this. Okay, so let me put it here. Yeah? Sorry, but we have to manage the space and we have to retain this data. So 1/2 is zero point 0.5. Let me put the 0.5. Then cross multiply by 8.478. 8.478, right? Then this x we retain the x, then we this whole thing here we transfer there, yeah, it becomes positive. So plus 478.038, right? So we have um to execute this, yeah, 0.5, 8.478. So we pull out again our calculator and it's still here, 8.478 times 1/2 or zero point 0.5. What do we get? 4.239. So here, 4.239. We get it down. This whole thing here is 4.239. Again, 4.239. Then 4.239 plus what? This one, yeah? 478. 478.038, right? So it should be greater than 478. So it is 482.27. 482.27. So the whole thing here, the x is 482. Also, we add this plus 478.038 equals x. So now the x, we put it here, the x or the enthalpy of fluid at the 114 degrees centigrade is nothing but 482.28. Now we rounded that off. uh, 482.28. 482.28. So this one is the enthalpy of fluid at 115 degrees centigrade. So let me put that here. So we'll change this into black. 100, what's this? 482.28. So here, yeah, this one. 478.038. This is 414. So now at 115, it is 482.28, right? And the saturated temperature is 115 degrees centigrade fluid. So it is fluid form because it's a wet feed. Yeah, fluid. HF means enthalpy of fluid. No? Enthalpy of saturated fluid. Okay. So let me get this. If we are matching with my old notes, enthalpy of fluid at 115, 482.28. So where's that? Enthalpy of fluid. Oh my God, it's correct. Yeah. Enthalpy of fluid at 115 by interpolation, or maybe there are other tables that are giving exact. So, but here we interpolated 482.48. What did we get? 482.28. 48.02. So we get, no? we get 482.28 482.28. Now it doesn't matter, yeah. 482, 482.4, 482 point, yeah. If you round off this, 482.3. So this one also 482.4, yeah, or 482.5, yeah. So between 482.5 and point 3, not so much of a difference, yeah. So it's okay, you know. So again, I would like to use the old notes so that it's because it's already calculated. We just use later the 482.48 or 482.4. Yeah. So because it's already there. Yeah. So what I'm after is this the calculation. Yeah. So the question is, what is the total heat now being supplied to the dryer? So I told you there are three heats involved. One is this, yeah. One is the heat required to evaporate the moisture, right? Number two, the heat absorbed by the sand from 30 to 115, because the fluid is 30 degrees centigrade up to the wet feed of 115 degrees centigrade. No? So there's a delta T. Yeah, because the formula is here. Yeah? So for the heat transfer, Q equals mCp delta T. Yeah. So this one is just the MH. Yeah. So the formula here is Q. One is M delta H. Right. So let us check the unit kilogram per. I think per hour we have per hour. Right. And then H is kilojoule per kilogram as the unit of energy. Yeah? So kilogram and kilogram, what you will be left with is kilojoule per hour, which is the unit of power or heat in kilowatt. Yeah, you can because this energy now, energy per unit time is power. So you can convert this into kilowatt. If you convert hour into seconds, you can get kilowatt. Yeah. So that's the second. The third is this one. Yeah? So the third heat is heat absorbed by the moisture that remained in the sand. Yeah. So meaning there's a sand after the dryer. No? Here is the rotary dryer. Here is the feed, and here is the product. Now, when the sand comes here, yeah, there's a sand here. Yeah, the sand still it has some moisture, and what is the moisture? 0.5%. Yeah. So here we are calculating the heat absorbed by the moisture that remained in the sand. Okay. So we will do that. Now we can calculate that the remaining moisture in the sand. Yeah. So with these three heat that is going to be calculated, then we will get the summation of this, and then we will get the heat output. The output of the heater going to the dryer as an input. Now because there's an efficiency, meaning we have to add this first to get the total. Now we go to the number one to make it quick. First, the heat required to evaporate the moisture. And what is this all about is the heat required to evaporate the moisture, meaning we have this formula. Now, so if this is the Q1, so Q1 now is the mass, yeah? So mass of the 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 sand, no? I mean the water evaporated, the moisture that is evaporated times the delta H. Again, so mass that is evaporated times the enthalpies delta H. So what are the enthalpy? The enthalpy there is the enthalpy of gas at 100, right? 100 degrees centigrade minus the enthalpy of fluid at the feed, not enthalpy of fluid at 30 degrees centigrade. Let me repeat that. Yeah? So we will use a pen that is more striking in color. So let me have this. So Q1 is the referring to the heat that is required to evaporate that amount of water. Yeah, what is the amount of heat that is required to evaporate that water? That water or mass flow of evaporated water, yeah, or the moisture that is being extracted is this, the 1397.85. Where do we get this? We get this from ME is F minus P. Must flow out at the feed, must flow at the product. We know this is 20,000 kilogram per hour, and this one is 21,397.85. So we have a difference of 1,397.85 kilogram per hour. So we have to multiply that into um, enthalpies that are concerned. First is enthalpy of gas at 100. Why 100? Because 100 is the evaporating temperature, boiling point of water before it evaporates. So it's 2676.1 minus, that is the enthalpy of fluid at saturated point, like the initial uh, temperature, that is 125 point, is that 79 or 19? 79. Yes. So the unit is here. Now the unit of enthalpy as an energy is kilojoule per kilogram, meaning the work done, or the energy is ability to do the work, kilonewton per meter is kilojoule for unit mass, a kilogram. So kilogram and kilogram will be cancelled out. All will remain is kilojoule per hour. So if we multiply 1,297.85 by the difference of these two, that is the Q1. That's the amount of heat needed to evaporate this amount of mass flow. Yeah, with the concerned enthalpies at 100 degrees centigrade saturated and 30 degrees centigrade. So we will have here 3,000. Is that 500? Yeah, 564. 3. I think it's 3 million. 564,000. 951 kilojoule per hour. Okay, so kilojoule per hour. Now that is Q1, right? I think it's clear, very clear to us what is this heat all about. It's the heat required to evaporate that water. Yeah, from here, from this internal energy in enthalpy. No, feed the minus product is the mass, and then is the difference in enthalpy. It's at 100 degrees centigrade, so we can get the Hg. This is at um, 30 degrees centigrade. We can get the Hf. So this one Hg minus Hf is Hfg. So in the Ts diagram, Ts temperature entropy. So if that is the temperature entropy, here is the critical point. So temperature here, yeah, temperature here is the fluid, right? So here is the fluid line. This is the vapor line or steam or gas saturated. No, so here uh, it will, yeah, so it will be like that. Yeah, like that. Yeah. So what I'm saying is 30. Yeah. So if we scale this at 0, 0. So if this is 0, then maybe 10, 20, 30. Yeah. So at 30 degrees centigrade, you can get here. Yeah. You can get the HF. Then the other one is, let me have this more steeper. Yeah. So 30, what is the other one? 100. Yeah? So if you continue this, if it's 100 degrees centigrade, so you can project here, right? So 100 degree centigrade because saturated gas, Hg. This one is HF. Yeah. So you can get the enthalpy, which is this, Hg and HF, right? Okay. So I think it's clear. Now the other one is heat absorbed by moisture that remained in the sand. Yeah. So I think it's labeled or tagged as Q2. So here, the formula is easy, right? So this is mass of the feed, right? Mass of the feed, and then this is uh, the 20,000 kilogram per hour, and the other is uh, what is that? Is that Q3 or I think we Q2 Q2 or is Q3? Q1 Q2 Q3. Or yeah. Q2 is there and Q3 35669. Where did we get that? Yes. Yeah, 35669 Q1 Q2. Let me go back here. Q2. Yeah, here. Yeah. So Q2 is this, right? Q2. This is Q3. This is Q2. Yeah. So Q2 is heat absorbed by sand from 30 to 115. From 30 to 115. Do we have that here? From 30. Yeah, this one. This is the rather the Q2. Yeah, Q2. So Q2 is the heat absorbed by the sun from 30 to 115. So that if there's a change in temperature, there's a heat transfer. So the formula is the general formula for heat absorbed and heat rejected. Heat transfer is mCp delta T. Yeah. So M, what is M? Is we have this what is M? Kilogram per hour. Then this is I'm checking the units, right? So units check, unit check. Cp is kilojoule per kilogram Kelvin or degree centigrade. There's no problem. And here delta T is Kelvin if you want to make it an absolute. So Kelvin and Kelvin will be cancelled, kilogram and kilogram will be cancelled. So what will remain is the kilojoule per hour, which is what we are going to have. Yeah, but right now, in this heat absorbed by the sand, we have 0.995. What is this? 0.995 because we have a moisture content of 0.5%, right? So 0.5%, we have 99.5% dryness. Now, so we can convert this into decimal 0.995 because it's decimal. So this 0.995 is this, right? So this is the percent dryness uh, of this, yeah. So we have to multiply this, yeah, because it's not purely dry. It's not 100%. If it's 100%, it's 1, right? But it's not 1. It's 0.995 multiplied by the kilogram per hour or the mass flow or weight per hour. So we will have this, yeah, 19,900. Then given in the problem is the CP of the sand. Yeah, yeah, CP of the sand, 0.21 BTU per pound per degree Fahrenheit. Let me check if we can get a direct CP of the. Let me keep that direct. What is this? Direct value of the CP, right? So here CP of sand in SI System International. Wow. Here, look at this. We have 780, yeah, if it's 0.186, but we have this 0.21, right? The BTU per pound mass degree Fahrenheit, it says BTU per pound per degree Fahrenheit. Let me check this. What is this? Alta. Uy. What is our given? I think we have a given 0.21 BTU per pound mass degree Fahrenheit. Oh yeah, this one, yeah, pound mass. Yeah, so BTU, look at this. BTU per pound mass degree Fahrenheit. This one, huh? So this one here, BTU per pound mass degree Fahrenheit is equal to 780, I guess. Let me check. Uy. Yeah, BT at this one. Oh, that is salt. My God, what is happening here? So here, CP of sand, yeah, sand, yeah, 780 is 0.18. So there's a difference here, right? So if you have 0.21, it becomes uh, 881. If you have 0.186, it becomes 180. But the thing is, according to the problem, it is 0.21. So we can use this, right? We can use this, yeah. We can use this, the equivalent of 0.21